professor.
Yeah.
And he's from Zhejiang University in Hangzhou in China. And he's gonna have a presentation about constructing blocking layer on polyamide non-filtration membrane surface via charge inversion for enhance the lithium selectivity of magnesium.
Okay. So I show my screen now. So, good morning, everyone. I'm Lin Zhang from Zhejiang University. Thanks for Professor Zhou introduce. Today, I will present our recent work on constructing blocking layers on polyamide nanofiltration membrane surface while charge inversion for enhanced lithium selectivity of magnesium. Okay. My presentation includes why we do this work, and how we do those membrane and the main conclusions. The separation of monomer and divalent mixture salters is very important. What you can extracting lithium from Brain Lake, treat industrial waste water, improve the effects of desalination and purification draw water. Among the separation of monomer and divalent mixtures salters, lithium ion and magnesium ion separation are most urgent needed for the demand of lithium battery keeps growing. In a typical lithium extraction process, lithium and magnesium separation is a key step, but the adsorption and electrochemical methods are higher energy consumption. So we know nanofiltration is a very promising membrane separation technology and show a very high flux and selectivity. And selectivity, the operation pressure is lower than reverse osmosis membrane. So energy consumption is lower too. The common polyamide nanofiltration membrane is prepared by interfacial polymerization between piperazine and trimethyl chloride. After the residual chloride, the residual acyl chloride groups has been hydrolyzed as carbon oxygen groups, and then the membrane surface is negative charged. Based on donor effect, commercial nanofiltration membrane is suitable for separating monomer and divalent anionic mixture salters, such as sodium chloride and sodium sulfate. So nanofiltration membrane with positive charged surface is very important to separating lithium and magnesium cations. So here we design 3 methods to modify the negative charged surface of commercial polyamide nanofiltration membrane. To avoid to broken the thin skin layer of nanofiltration membranes, the 3 methods are very moderate, using water or alcohol as solvent at room temperature to graft PI on membrane surface, and the imine groupers of PI will give membrane surface positive charge. The first work is modify polyamide nanofiltration membrane using water as solvent. Graft PI graft PI on nascent polyamide membrane. Polyamide membrane surface. After interfacial polymerization, the nascent polyamide nanofiltration membrane has emerged into PI aqueous solution, and the imine group of PI react with residual acyl chloride groupers, and the surface covered by PI and is charged code inversed from negative to positive. We test the change of rejection of lithium and magnesium ioners of the modified nanofiltration membrane with different PI concentration. This figure shows the test result, and we can find that there are little increasement of magnesium ion rejection with rising the PI concentration. But the rejection of magnesium chloride not very high. Why? We guess that the most residual acyl chloride groupers was hydrolyzed when it contacted with PI aqueous solution. And I will show the proof in the later slides. Now that the water causes the hydrolysis of residual acyl chloride groupers, so we use alcohol as solvent, solvent to modify polyamide membranes and graft PI on its surface. This procedure is same with using PI aqueous solution, except for solvent. So by this method, we wish to improve the PI grafting ratio. We verified the hydrolysis ratio of residual acyl chloride group on the nascent polyamide membrane. Nascent polyamide membrane surface after contact with water and alcohol respectively by EDEX, FTI, and XPS. From these results of EDEX, we can find the oxygen contained on membrane surface contact with water is higher than that with alcohol, and the chloride contained on membrane surface contact with water is lower than that with alcohol. The results of FTI and XPS are similar with EDEX, so the hydrolysis degree of acyl chloride groupers was inhibited by using ethanol as solvent. For PI is a hyperbranched polymer, and there is an obvious steric hindrance when it has grafted on membrane surface. So we try to graft the PI with different molecular weight, and we measured the carbon oxide and imine groupers and imine groupers density on those membrane surface by diol adsorption. And when PI molecular weight decrease from the 10,000 to 600 yeah. The carbon oxide group density on membrane surface decrease, and the imine groupers density increase. The results prove the PI with lower molecular weight can improve imine grafting density, and the PI steric energy also shows same trend. The zeta potential and the water contact angle of PI graft membrane with different molecular weight was listed in this figure. The membrane graft with Pi 600 is the best, and the isoelectric point of bare polyamide membrane is 3.42, and the membrane graft with Pi 600 rose to 8.2. So we got a nanofiltration membrane with positive charged surface. We calculate the surface energy bare by DLV model, and the surface positive charge is strong. The membrane surface energy bare is higher, and the magnesium ion rejection is higher too. So it's proving the donor exclusion is a king ruler for separating monomer and divalent ioners mixture salters. And this figure shows the separating factor of lithium and magnesium ioners through bare and modified polyamide nanofiltration membrane. And the selectivity of lithium and magnesium ion was improved to 12 through the membrane graft with Pi 600. And the positive charged membrane has another advantage. For the surface electrostatic interaction, the calcium of ioners cannot deposit on the membrane surface, and the anti-fouling performance was also improved. The membrane was washed, the flux and the rejection can remind the original value. For the higher positive charge can improve the lithium and the magnesium selectivity. So we should increase the positive charge density on membrane surface fusion. So we use EDC and NHS to catalyze amidation reaction of PI with carbon oxyl group on membrane surface. The procedure is still the same with the other two modification procedure, except for using EDC and NHS and PI aqueous solution. This slide is SEM of bare polyamide, modified polyamide membrane with PI aqueous solution and with PI ethanol solution and EDC NHS catalysis membrane. And the images shows that all the three modified membrane morphology are similar with bare polyamide membranes. And it means that the modification method will not broken membrane skin layer. The AFM was used to measure the membrane morphology, roughness, and thickness of bare polyamide membrane and three modified membranes. And the result shows the modified membrane roughness and thickness are unchanged. So we can from 4 figures. And the pore size distribution of bare and modified polyamide membrane were obtained by by measuring the rejection of silver salters with different molecular different. And the precise distribution has no obvious change. The precise distribution was similar before and after modification. And the carbon oxygen and imine groupers on bare and modified polyamide membrane surface have been measured and compared by FTIR, XPS, and charged dye adsorption. It can be found that the bare membrane had the highest carbon oxygen groupers density. And the membrane modified with EDC and NHS had a highest imine density. So the result shows that the surface content of imine groupers was gradually increased after 3 modifications. We investigate the water contact angle, zeta potential, and lithium and magnesium selectivity. The EDC and NHSPI membrane shows the best performance. The reason is that the EDC and NHS can catalyze all carbon oxygen groupers with PI, even the carbon oxygen groupers in membrane surface valley. So the membrane's positive is the most strong of membrane with modified EDC and NHS and PI. To verify that the surface charge playing a key role for monomer and divalent ion separation, we take 2 commercial nanofiltration membranes, NF270 and NF90, to measure their charge group density and pore size, and test the selectivity between chloride and sulfate ioners mixture salters. AFM immersion shows that the thickness of NF90 is more than the NF270, and the pore size of NF90 is smaller than that of NF270, but carbon oxygen group content of NF270 is higher than that of NF90. It means that NF90 has a smaller pore size and a lower carbon oxygen density, but NF270 has bigger pore size and higher carbon oxygen density. The chloride and the sulfate ion separation result proving that NF270 has a 20 times selectivity of NF90. So we can say the higher charge density is more effective than higher density in improving the selectivity of monomer divalent ioners. So based on this work, we conclude that electric charge property is a more crucial factor than density for improving mixture ioners selectivity. And we also obtain 3 methods to improve the polyamide membrane surface positive charge. And among them, the EDC NHS catalysis is the best one. all those surface charge inversion methods are facial and higher infections, and the resultant membrane has a higher performance. So thanks for your attention. Comments and question? So maybe I stop share. Oh, okay. Our magnesium and lithium concentration is 2000 ppm. And the ratio of magnesium with lithium is 20.
Yeah. Professor Zhang, while people are typing their questions, I would like to ask you a simple question. It was very nice research, very interesting research. But I found out that in one of your experiment, you use 2000 ppm mixture solution of magnesium and lithium chloride solution. The ratio of magnesium ions to the lithium ions was 150. So my question is, what's the reason why you select such a high ratio to test your membrane?
Because in China, Brain Lake, the magnesium concentration is more higher than the lithium, and we talked with the plant in Qinghai province. So do you know?
Yes.
They tell us the pre-treatment for extracting lithium is very long, and we just need the separate magnesium and the lithium. The lithium the concentration is very low, so I just using these concentrations.
Okay. Well, it sounds very logic.
Thank you.
My question is answered. Thank you.
Thank you very much.
Oh, Professor Zhang, there is another question.
Okay.
Perhaps Dr. Zhou can speak it out for you, but if he didn't, I will help him to speak up. What is the scalability level for flat sheets, hollow fiber membranes, and spiral?
Spiral. Not a hollow fiber. No. Is a plain.
Yeah.
We flat sheet. We use a flat sheet, but I think the just a second. Okay. What is the scalability level? We just measure the flat sheet membrane. We do not hollow fiber, so I can give you suggestions. So.
Dr. Zhou, can you speak out the questions for Professor Zhang?
I have a small question about your surface modification. And you increase the positively charged membrane for the lithium magnesium selectivity. And I little bit about concern for the organic matter fouling, because there are lots of organic matter in the negatively charged. So if you increase the positive charge, there will be some interaction between organic matter and the membrane surface. There will be critical issue for the after the stability of your surface modified membrane, because if there will be fouling layer, the lithium magnesium selectivity will be decreased. So what's the strategy of about the organic matter fouling?
So we just measured the calcium chloride, and we didn't measure the sulfate magnesium and calcium.
Professor
So-
Zhang,
so, yeah.
sorry for interrupting. The question from Dr. Zhou was that because you have a surface positive charge,
Yeah.
it might be fouled by organics in the aqueous solution. Because you didn't test the organic fouling, perhaps next step you could check it out. And when you have a real brine, salt lake brine solution which contain some foulant, because your surface charge is positive, there's a lot of negative charged organics in the brine.
Oh, okay. I see.
It might foul your membrane, so you have to check it out.
Yeah. But I show these slides. Okay. I show just a second. Just a second. I show these slides. Just a second. Okay. We just to treat this step. Here, maybe there is no any organic organic.
It's very
fouling.
clear. Yes, there is
Yeah.
low organic fouling. Yes, so
Yeah.
it's logic. Yeah.
Yeah.
Thank you.
Okay. Thank you.
There is question in the chat room.
Okay.
Dr. Zhou, can you read out the question to Professor Zhang? Then we can continue with the next speaker. Thank you.
Okay. Thank you. I will answer on this the chat window. Okay.
Yeah, please go ahead, but don't take it too long.
Yeah. So maybe the next speaker, Professor Rowe.
Is it my turn? I think.
No, I think there's another one.
Another one.
Shuang Han. Yeah.
Yeah.
Hello, Professor Zhang. I have prepared the video and send it to the host. Could you play the video?
Okay.
Okay. Yeah.
Shuangqiao, can you open your video so we can see you? Then can you share your screen?
Oh, sorry, need to note it or
No, because I think the stream say she's not here. So you can share your screen. There is a 共享屏幕，在下端有个共享屏幕，你共享一下你的这个，共享一下就行了。你看能不能行
？OK。
哦，那这个不行了，我们他不行，我们就下一个了。那不行，那不行，我们下一个呗。
OK。Oh, can you
No. Okay,
Oh, okay, okay.
perfect. Go ahead, please.
Okay.
Okay. Good morning, everyone. My name is Han Shuangqiao. I'm from Zhengzhou University of China. It's my great honor to have the opportunity to attend this conference. The topic of my report today is Covenant Organic Framework Mediated Nanofiltration Memory for high nano-ordinate salt selectivity. Next, I will report from the three of specs. First of all, I will show the resource background. Water scarcity has become a serious challenge at our times. As an energy-saving water purification technology, membrane-based separation has been broadly implemented for water-related treatment thanks to high separation selectivity and environmental benefits. In specific, endowed with a wide range, about 0.522 nanometers, the applications of nanofiltration membranes have intended to diverse fields. The commercially available nanofiltration membranes are generally dominated by thin film composite membranes, in which polyamide nanofilms were constructed using interfacial polymerization between diamides in aqueous media and also colorized in organic media. However, the rapid polymerization is inevitable needs to a thick and dense selective layer, which poses a major impediment for breaking through the trade-off equation between the permeability and selectivity. Incorporation of multifunctional nanofillers, next MOFs, and so on. With a polyamide film promises for correction of additional water transport steps, thereby enhance the water promise. However, the weak polymer affinity of inorganic or hybrid nanofillers is inevitable, leads to Fermi non-selective interfacial cavities. Besides, the key problem of polymers nanomaterials fails to process the poor operations that match the process range of nanofiltration membranes. Recently, the emergence of COS is expected to afford a potential solution to the above-mentioned problems, endowed with all organic components connected by robust covalent bonds. The stability and polymer affinity of COS are superior to MOFs. Furthermore, the reported COS feature uniform pore apertures ranging from 0.8 to 5 nanometers, which show a high multi-degree with the process of nanofiltration membranes. Herein, a hydrophilic layer of COFs, termed as TPP-DMTP COF, was introduced onto polymeric substrates prior to an IP process aiming at rationally design of high-performance COF-modified membranes. In detail, the prepared TPP-DMTP COF utilized as the nanofillers were positioned atop the substrate will review a set filtrational method, followed by IP technology. In our work, a series of characterizations were applied to analyze the physical-chemical characters of the TPP-DMTP COF. The XRD curves of the powders show the high fertility of the prepared COF. Besides, COF particles have a uniform spherical structure with size ranging from 15 to 100 nanometers. A TEM image of COF particles also shows the same spear-like structure without the formation of aggregates. The surface of pristine polyamide membrane presents a nodal structure with tiny packet spherical particles. With the further increase of curve knotty mass, surface structure of the curve modified membranes show a marked change to consistence of bubble-shaped and nobular structures. This change in the microstructure of the polyamide layer is mainly because of the existence of curves affecting the PIP diffusion rate in the vicinity of the organic boundary. Besides, the incorporation of a curve layer was found to decrease the thickness of the membrane. The FTIR and XPS characterizations were explored to analyze the chemical structure of as-prepared polyamide nanofilms. The cross-linking degree of the control polyamide membrane and curve-modified membrane were 64.3% and 56.5% respectively. The presence of curves leads to the formation of polyamide networks with a lower cross-linking degree, reveals a higher number of unrelated also connected promotes the production of more corpuscle and growth through hydrolysis. Zeta potential was measured to assess the surface charges of as-prepared polyamide membranes. Notable, the incorporation of curves leads to a polyamide film carrying more negative charge, which is probably due to the presence of curves leading to more corpuscle growth. Besides, increasing the curve loading was found to decrease the water content angle for curve-modified membranes. The decrease in water content angle mainly arises from the combination of the introduced curves and the increase of corpuscle growth. Also, the separation performance of the curve-modified polyamide membranes was studied. After adding the curve, the best-performing polyamide membranes achieves a high water permeance, which is fourfold higher than that of preceding polyamide membranes. Despite an obviously improved water permeance, the sodium sulfate rejection of the modified polyamide membranes remains almost unchanged. Besides, the flows of curve-modified membranes linearly increased with applied pressure, consistent with the stability of modified membranes. Of as-prepared membranes was assessed by the measurement of salt rejection. The per polyamide membrane exhibited a selectivity coefficient of chlorine I or sulfate I was about 20 to 30. The introduction of curves not only improves the negative charge of polyamide membranes, but also increases the porosity of the membrane surface. Therefore, the selectivity coefficient of chlorine I or sulfate I is as high as 18.4. MD simulation was employed to compute the diffusion rates of PIP molecules in the aqueous phases before the formation of polyamide films with or without the incorporation of coarse particles. Based on the acid relationship, the diffusion coefficients of the PIP molecules were marked from the mean-square displacement curves. The results showed that the diffusion rate of PIP molecules in the presence of coarse nanoparticles was 25.3% lower than that of PIP in water solution, which confirmed our predictions in the interpretation of the high permeability of curve-modified membranes. To review the formation process of the polyamide layer, DPD simulation method was employed. The PIP monomers migrated to the water or hexane interface. Besides, for curve-modified membrane, an amount of PIP monomers absorbed onto cloth layers rather than diffused to the water or hexane interface, indicating that the presence of cloth particles reduced the diffusion rate of PIP monomers. Besides, note that much more errors of low density PIP monomers can be found with the presence of cloth, which is in good augury with environmental results. In summary, TBP-DMTP curve is captured precisely controlled pore diameter and vertical nanometer channels, different from inorganic particles. The organic covalent bond makes cloth exhibited superior affinity with polymers, which prevents the formation of interior defects in membranes. The diffusion rate of PIP monomers in the cloth modified membranes is 25.3% lower than that in the water. The selectivity coefficient of coronary eye or sulfate eye is as high as 18-fold. Cloth modified membranes has greater potential in separation molding or diluent salts. Finally, I would like to thank my supervisor, Professor Zhang, for his cultivation and encouragement, Professor Zhu for his contribution in environmental design, and Professor Mai from Jiangnan University helped with the calculation of simulation. At the same time, I also appreciate the support and help of other students in our research group. That's all. Thank you for your listening.
So, thank you, Shu Qiao presentation. So, we have a time for one question. So, any question?
Okay.
Shu Qiao, stop your share. Stop your share. 停掉你的共享屏幕。舒乔 ，Hello， 舒乔，stop your share screen.
Oh, okay.
So, can you see chat window? One question for you, or two questions. How is the curve loading quantified? Why is the contact angle increase for curve loading above 6.4?
Okay. Thank you, Professor Zhang. I think in this case, the curve loading is the amount of suspicion to minimize the loss of curve. No precision fabrication was adopted to fix curve particles for half an hour. Therefore, the loss of curve is not included here. The other answers is the curve capacity of on the membranes has an optimal value. So when the loading capacity of curve is greater than the optical value, the particles can be aggregated on the membrane, resulting in the increase of the surface roughness, and therefore the water contact angle becomes larger. Thank you. That's all.
Okay. Great. Thank you, Shu Qiao. For our time is over. So we any question we can ask by chat window. So next speaker is Dr. Rao. Rao is from Korea Institute of Civil Energy and Building Technology, Republic of Korea. His presentation is facial surface modification of polyamide reverse osmosis membrane using UV photo oxidation for improving permeability and residual natural organic matter fouling. So Is your time, Dr. Zhou?
Okay, thank you for a kind introduction for me. Okay. Can you see the screen? Okay, this is a great honor to have opportunity to present my research in desalination conference, and entitled Facile Surface Modification of Polyamide Reverse Osmosis Membrane using UV Photooxidation for improving permeability and reduce natural organic matter fouling. So this is the content of my presentation today. I'm going to have a talk with a brief introduction. Water shortage and concern over anthropogenic pollution is necessitating increased reliance on impaired water supply to meeting growing municipal, industrial, and agricultural water demand. Alternatively, membrane-based processes such as MF, UF, NF, RO, and MBR are gaining a great attention due to their strong ability for applicability, water quality management, and production cost. Among them, NF and RO are generally used for drinking water treatment and ultra-pure water production and desalination processes due to their high salt rejection ability. However, in the case of NF-RO, membrane replacement, cleaning, and operating cost account for a significant portion of the total cost. Therefore, developing and securing technology to reduce them has high market competitiveness, and tons of research have tried to improve performance of the membrane processes. As you can see left slide, there is a strong trade-off between permeability and rejection of polyamide membrane, which is the most generally used for NF and RO membranes. For example, higher permeability generally has lower rejection, and lower permeability generally has higher rejection. Therefore, many strategies have been evaluated for improving membrane performance via surface modification techniques such as doping, coating, or grafting of nanoparticle or brush-like polymer for being upper bound of this strong trade-off. However, there is a limitation because such trade-off are attributed to the inherent structure limitation formed by interfacial polymerization of the polyamide membrane. Therefore, to overcome this limitation of polyamide membrane, a novel approach to modify the inherent structure of the polyamide membrane is crucially required. Although increased salt rejection is considered more critical for seawater desalination application, increased permeability without loss of salt rejection is also potentially beneficial for drinking water treatment and brackish water treatment, because such advance would improve energy efficiency of membrane processes while still achieving water quality goals. So in this study, we hypothesized that the subtractive surface modification, not additive approach, could improve performance of membrane. The idea is direct absorption of short wavelengths of UV induce the sequence of CM bond, leading to formation of two radicals. The produced radical then abstract a proton and forming aldehyde and amine groups. Aldehyde group can also be converted to carboxylic group with UV irradiation and short wavelengths in the presence of oxygen. The objective of this research is to validate a novel surface modification technique using short wavelengths of UV irradiation, which can increase permeability and reducing fouling without decreasing salt rejection, using these produced other ionizable carboxylic and amine functional group on polyamide membrane surface. So let's move to material methods section. Photooxidation of RO membrane was conducted with 285 nanometer of UV LED in an aqueous environment with a collimated beam apparatus. Left figure shows the apparatus, which was fully immersed in a DI water bath to prevent polymer aging effect of the membrane and reflection of water-air interface. The intensity of incident irradiation at the end of collimated tube was measured by calibrated radiometer. The UV dose delivered to the membrane surface varied by changing of UV exposure time. The active layer of our membrane were irradiated at 3 different UVB doses to investigate the effects of UV irradiation on polyamide membrane and cellulose triacetate membrane. The samples are referred to as PA12, PA25, and PA50, where the letter indicates the membrane type, the number indicates UV dose. This is an analytical tool to investigate changes in surface characteristics of membrane in terms of UV irradiation. XPS and FTIR were used to analyze surface functional group, and SEM AFM to analyze surface morphology and roughness. And contact angle and zero potential were used to analyze hydrophobicity and charge characteristics. The performance of pristine and UV irradiated membrane was systemically evaluated using 2 lab-scale membrane units. First, permeate water flux and salt rejection were evaluated using a dead-end steel cell under low pressure used for measuring the permeability and salt rejection using 10 millimole of sodium chloride and magnesium sulfate and boric acid as a first step toward advanced of UVB light treatment for membrane, including selecting the target UVB dose. Rejection of non-ionic boron occurs only due to the size exclusion, while electrostatic repulsion and donor exclusion occurs for other ions. Thus, boron rejection were measured for indirectly representing pore size of polyamide membrane. The fouling propensity and sodium chloride rejection of pristine and UV irradiated outer membrane were separately evaluated using a lab-scale cross-flow unit using feed water containing molar organic foulant, Swanee River NOM, and phenolic perfluoric acid at a high ionic strength under high pressure to represent more realistic scenario of membrane processes. The fouling propensity of our membrane were evaluated by mass of dissolved organic foulant and hydrophobicity of organic foulant and resistance value. The fouled outer membrane were collected after cross-flow experiment and then soaked in 0.1 normal sodium hydroxide for 10 hours. The amount of dissolved organic foulant and their specific UV absorbance at 254 nanometer were determined using a total organic carbon analyzer and UVB spectrometer, respectively, using following this equation. The membrane resistance and resistance due to NOM fouling were calculated from the mass permeation flux measured during the membrane filtration using a resistance in series model. So this is the surface morphology and polyamide and CTA membrane. As you can see the figure, PA50 membrane turned a slight yellow color due to chromophore oxidation compared to white color of pristine PA membrane. SEM images of the pristine PA membrane show ridge and valley structure, which are typically observed in fully aromatic polyamide membrane. And higher UV dose cause a gradual collapse of ridge and valley structure, which is known to be polyamide moieties of the membrane. In contrast with the result of polyamide membrane, UVB pre-treated CTA membrane exhibit no color change nor change in surface morphology. XPS provide insight into the changes in the surface functional group on the polyamide membrane. Minimal changes in XPS signal was observed for the CTA membrane with UVB pretreatment. However, in the case of polyamide membrane, as the UVB dose increased, the O and N spectra of the polyamide membrane shifted slightly to lower binding energy, indicating that the conversion of CN bond to the carboxylic and amine groups on the polyamide membrane surface. And also IR peaks corresponding to NH stretching of the amide linkage and amide 2 band decrease with the UVB pretreatment of the polyamide membrane, and the IR peak corresponding to CO stretching of the ester group intensified slightly after UVB pretreatment, indicating that polyamide active layer were oxidized and cross-linking to a lesser degree as UV dose increased. The reduced cross-linking is attributed to the membrane oxidation induced by photoreaction of CM bond. Overall, these observations imply that polyamide moieties on membrane surface were gradually converted to the carboxylic and amine group with UV irradiation, which affected the region valley structure of pristine polyamide membrane. These are the potential and contact angle result of our membrane. As you can see left side, the electronegativity of UV irradiated polyamide membrane gradually increased as a function of UVB dose. The 12 joule per square centimeter UVB reduced the surface contact angle from 40 degrees on the pristine membrane to 33 after treatment. Higher UVB pre-treatment dose rendered the surface only slightly more hydrophilic. In addition, surface contact angle of pristine and UV irradiated polyamide membrane were not significantly changed after 8 weeks aging with the DI water, indicate no significant hydrophobic recovery of the photo-oxidized polyamide membrane over time. However, also no impact on surface contact angle or zero potential were observed for the CDM membrane after UVB pretreatment. As you can see, right side, CDM membrane were insensitive to UVB pretreatment. However, the permeate flux of pristine polyamide membrane was 21 nmH, applying the UVB at 12, 25, 50 joule per square centimeter onto polyamide membrane before the flux experiment increased the permeate flux to the 29 and 40 and 531 nmH. This is a 34 and 85% increase in the water flux for 12 and 25 joule per square centimeter UVB pretreatment respectively. Surprisingly, these flux increases were accompanied by negligible changes in NaCl rejection between pristine and pH-12 and only 7% decrease for pH-25. However, boron rejection decreased as UVB dose increased from applying 12 joule per square centimeter, indicating that the pore size of PA membrane get opened by UVB radiation. The fouling propensity of pristine UV irradiated polyamide membrane were compared using two model organic foulant with the left scale cross-flow filtration system. The left figure shows that initial permeate flux were the lowest with the pristine polyamide membrane and increased with UVB pretreatment. In addition, a higher UV dose alleviated the permeate flux decline by organic foulant and decreased the amount of dissolved organic foulant during 15 hours. The gradual specific UV value decrease NOM foulant indicates that the alleviation of organic foulant of UV irradiated polyamide membrane is attributed to decreased hydrophobic interaction between NOM and polyamide membrane surface due to increased electrostatic repulsive force. Furthermore, the resistance of polyamide membrane and model organic fouling layer gradually decrease as the UV dose increase. This may be attributed to the gradual decreased surface roughness of polyamide membrane as UVB dose increase. As you can see, right figure. Overall, these results support the assumption that UVB pretreatment of polyamide membrane could significantly reduce the natural organic matter fouling potential by reducing hydrophobic interaction, could thus be promising surface modification tool for alleviating the decline in the permeate flux. To summarize my presentation, we demonstrate that photooxidation by UV irradiation modify polyamide active layer, resulting in conversion of PA moieties to carboxylic and amine functional group and leading to an increased surface charge and hydrophilicity. UVB dose of 12 and 25 joule per square centimeter enhanced water permeability by 34 and 85% with negligible changes and 7% decrease in NaCl rejection. This is attributed to that UVB pretreatment of polyamide membrane increased membrane pore size. However, it occurs simultaneously with an increased membrane surface charge and donor exclusion, which is accompanied by negligible changes in NaCl rejection. UVB irradiation also led to lesser fouling by Swanee River NOM and phenolic formic acid in cross-flow tests, owing to reduced hydrophobic interaction between NOM and membrane. These results confirm that UVB dose appear to modify only a thin layer on the polyamide membrane surface, which favorably enhance the permeability and anti-NOM fouling without decreasing charged ion rejection. So to conclude my presentation, the physical-chemical characteristics of CDA membrane were insensitive to UVB radiation. And the UVB pretreatment of polyamide membrane increased the membrane pore size, surface charge, and hydrophilicity, thereby increasing permeability and reducing NOM fouling without loss in salt rejection. This surface modification using photooxidation does not make chemical waste and can be directly applied in row-to-row fabrication process of polyamide membrane for developing our membrane and also polyamide-based nanofiltration and photosmosis membrane. The merit of this surface modification is easy to control the strong trade-off between permeability and rejection of polyamide membrane with achieving water quality goals. Thank you for kind attention.
Okay, thank you, Dr. Rowe. So, any question? So, I have a question. How long your UV photo oxygen reaction on the?
Did you ask about the exposure time about
yeah,
UV?
Yeah.
It's about 20 hour for the 20 hour for the 12 joule per square centimeter, something like that.
Okay.
It's
so,
not too long.
Not too long. So this modification will not broken the membrane skin layer. So right.
Yeah, only a thin layer with oxidized and will be very improved the membrane performances.
Okay. So another question? If no, so we thank you, Dr. Rong, again. Thank you. Very nice presentation. Okay. So the last speaker in our session is Dr. Bingxin Gu, from Center for Membrane and Water Science and Technology, Zhejiang University of Technology. So Gu is here. Okay. So it's your time.
Hello everyone, my name is Bingxin Gu from Zhejiang University of Technology. The title of my report is Construction of Zip-8 Nanochannel Membrane for Efficient Separation of Molecules and Salts. In chemical production, the separation process accounts for a huge proportion of investment. Membrane separation is a new and efficient separation technology. There are many advantages about it, such as low energy consumption, sustainable development technology, and so on. However, the preparation of membranes with sub-nanopores presents a challenge for advanced molecular separation. Nanofluoride membrane with molecular ionic ultra high selective transport nanochannel is an ideal choice. for efficient separation. But the preparation of nanofluidics membrane involves complicated nanochemistry such as porous nanoetching, efficient exfoliation. In addition, the high energy consumption and limited membrane size remain challenging unresolved. Conventional materials for synthetic membrane are dominated by polymers, which have the advantage of superable film processability, wide pH tolerance, and so on. However, dynamic polymers chains are intertwined and tightly stacked, resulting in low free volume with polydisperse size. We know that the uniform process, abundant channel, and solid pore are conducive to the realization of high permeability, high selectivity, and stability of separation membrane. Move a porous crystalline material with regular pore structure have greater potential in this field. So we propose rather scaffold reinforced polymeric nanoparticle interfacial channel to construction membrane nanofluidics. Move can regulate the interfacial pore size, improve the porosity of the membrane, and form a rigid interfacial layer, inhibit the nanopore deformation, improve the rigidity of membrane pore wall, and the stability of membrane structure. The preparation process is shown in the figure. The orbital membrane have uniform pore size, abundant channel, and a solid pore wall structure. We first proved that these eight craters were successfully crossing surrounding the amorphous ZMP nanoparticles by 30 FTI and XPS. It can be seen from the surface and cross-section as in image. The ZIF-8 at ZMP membrane are defect-free and the nanoparticles are tightly stacked. The thickness of ZIF-8 at ZMP membrane top layer about 100 nanometer. Freestanding ZIF-8 at ZMP membrane was characterized by a high-resolution TEM and the crystalline region as a result of the initial growth of ZIF on ZMP nanoparticles. Meanwhile, the EDS shows that the ZIF is uniformly distributed on the top layer of membrane. Low field NMR was employed to study the status of water molecules in ZIF-8 at ZMP. The peak 1 and peak 3 are attributed to free water and confined water. Interestingly, the peak 2 for ZIF-8 at ZMP shifted to an upward relaxation time. The transverse relaxation time of the water molecules is correlated to the size of micropores. So, the C4 of peak 2 indicates that the formation of large interfacial nanopores between ZIF-8 and ZMP nanoparticles. Moreover, Figure C shows that the capillary picture of ZIF-8 at ZMP membrane maintained better than that of ZMP membrane, which were immersed in water. That means ZIF-8 at ZMP membrane with higher stiffness. In addition, the ZIF-8 at ZMP have much higher specific surface areas and larger internal nanopores. Compared with the ZMP membrane, both the Young's model and the hardness of the ZIF-8 at ZMP membrane was enhanced. Because of their advantages, The zip it at zinc membrane with excellent water permeance and selectivity. When the operation pressure is 3 bar, the water flux of zip it at the NP membrane will enhanced, which is 20 times higher than that of the NP membrane. The results suggest that the channel in zip it at the NP membrane are rigid and pressure resistant. Comparison of the eight at the NP membrane with the state of the other nanofiltration membrane showed that its water permeates outperformed all natural nanofiltration membrane. Therefore, at the NP membrane also exhibit excellent long-term stability. Although therefore it and NP have higher hydrophilicity and high negativity charge, it's unlikely to boast one magnitude improvement in water permeance. We found that there are two kinds of microbe exist in the move at zinc membranes. The small one is made from the internal sub-nanometer pores, and the new large one is produced from interfacial nanopores between nanoparticles. To verify the separation mechanism, we performed the molecular dynamics stimulation by molding a nano channel in zip 8 at a zinc membrane. It has a very fast flow rate, which is almost 2 orders of magnitude higher than that of the NP membranes. And the water permeance could be further increased with increasing the pore size. The enlarged ridge nano channel at a high speed will facilitate the water molecules quickly transporting through the membrane, resulting in an ultra fast nanofluidic flow. What permeates through a nanochemical in zip 8 at a zip membrane is 2 orders of magnitude higher than that through the NP membrane. This is because the soft polymeric interfacial power of the NP membrane is prone to distortion in the dynamic filtration process. By contrast, the nano channel of zip 8 at the NP membrane will reach the line was maintained well in the wall simulation process. Due to the nanochemical process of the DNP membrane is much larger than the hydrotic orange diameter. All of the inorganic salts are likely to transport through the membrane quickly. Thus, they food it at the membrane exhibit much higher selectivity to CR molecules and different inorganic salts. Therefore, it at the membrane maintained both much higher water permeance and selectivity than that of the NP membrane within 150 min filtration. Efficacy of this at the NP membrane is 3 times higher than that the NP membrane. Their results verify that the ZIP eta and ZMP membrane have broad application prospects in the filtration and concentration. In addition to ZIP and ZMP membrane, more proposed move will easily grow around the polymeric nanotemplate to prepare a nanofluidic membrane by this same method. Their membrane all exhibit similar power hierarchy and ultra-high water permeance. Finally, in this work, we have proposed a rigid scaffold reinforced polymeric nanoparticles interfacial channel. to construct water ultra-permeable nanofluidics in polymer membrane for the first time.
软的，然后是 with
Experimental and simulation round show that the superfast water transport in the membrane is attributed to rich and continuous interfacial channels in the membrane. This work offers a generic and better method to prepare nanofluidics membrane exhibiting ultra-high permeability combined with extraordinary selectivity. Okay, that's all. Thank you.
Thank you, Dr. Gu. Because the time limit, we have only one question here from the audience. There is, can you tell which is ZIF8 at ZNPMS in simulation? Can you tell? How can you tell? How can you make it sure that you in your simulation that oh, sorry, audience. Dr. Gu is not online, so we are closing this session. There is no question, no answers. Please get to the next session at 11 o'clock. Also, please remember that we will have a closing ceremony for the students, for young researchers. Take care because you might be selected as a awardee. Please, I will see you later. Bye. I will closing the ceremony, closing this session now. See you later. Bye bye.